Western Germany, 11th February 1945, at 0400 hours, Heinrich Roth of Geiger 26 wrenched his control column hard to starboard as his FW-190 thundered through the air at roughly 400 miles per hour, his arm burning with the effort while the stick only inched a fraction of a centimeter. The Focke-Wulf refused to respond, even as the Hawker Tempest on his tail slid smoothly into firing position with its 4 20mm guns already trained on his cockpit. The stick felt as if it were fused to its mount, demanding well over 60 pounds of force for the tiniest deflection. Roth understood with absolute clarity that he had minutes, if that, because his ailerons had effectively locked up at that speed. The British fighter behind him was turning as if it were flying at half the velocity, a performance that flatly contradicted everything Luftwaffe engineers believed about control at high speed. 3 seconds later, 20mm rounds shredded Roth's canopy. As his FW-190 tumbled toward the German countryside, he became another victim of a technological leap the Wehrmacht's leading designers had not anticipated. A small device known as a spring tab had given the Tempest control characteristics that overturned German assumptions about combat at 400 miles per hour. By February 1945, this aileron arrangement was inflicting severe losses for Luftwaffe pilots were killed in January alone in clashes with Tempests, most of them learning too late that their machines became nearly uncontrollable at velocities where the British fighters stayed fully maneuverable. That gap turned high-speed engagements from a contest of skill into near executions. The roots of Germany's deadly handicap go back to the summer of 1944, when reports first reached Luftwaffe headquarters about a new British fighter that seemed to flout aerodynamic limits by keeping light aileron forces at speeds where both the Messerschmitt Bf-109 and the Focke-Wulf FW-190 experienced control loads so severe pilots could not move their sticks enough to fight. Major Wilhelm Steinmann, commander of 2 Gruppen of JG-26, dismissed those early messages as exaggerations or pilot error, arguing that no single-engine fighter could preserve light control forces at 400 miles per hour because the aerodynamic loads at those speeds made large control impossible without hydraulic assistance, a solution that would add weight and complexity. No single-engine fighter could afford. Steinmann's certainty was born of long experience with Germany's premier fighters. The FW-190, despite its advances, demanded enormous physical strength at speed, with pilots often forced to apply 45 to 60 pounds of lateral force just to produce modest rolls above 350 miles per hour. The Messerschmitt Bf-109 suffered even worse. Its cramped cockpit limited the side force a pilot could exert to about 45 pounds, making full aileron deflection unattainable at combat speeds. That constraint had killed hundreds of pilots who, diving to escape Allied attackers, found their controls growing progressively heavier until they were practically immovable. The problem seemed rooted in inexorable physics. As velocity rose, forces on control surfaces ballooned, requiring ever greater human effort in creating the cruel paradox that speed robbed an airplane of agility until at top speed fighters behaved like straight-line missiles incapable of effective turns or rolls. German engineers experimented with fixes, fitting Flettner tabs to some Bf-109G examples, small auxiliary surfaces that slightly reduced control forces. But those measures offered only marginal improvement and were fitted to relatively few machines, leaving most Luftwaffe airmen reliant on brute strength and careful speed management to retain any meaningful control at high velocities. Engineers at the Reich's aeronautical establishments in Augsburg, Dessau and Rechlin had long accepted that there was no practical way to cut control forces at very high speed without hydraulic assistance, treating heavy stick loads as an inevitable trait of This belief was dramatically overturned when the Hawker Tempest entered service in April 1944 carrying a device German designers had not factored in, a spring-tab aileron arrangement that automatically reduced control loads as speed climbed, letting British pilots retain near-trainer levels of stick sensitivity at velocities where German airmen could barely budge their controls. The mechanism was straightforward in concept. A small auxiliary surface hinged to the trailing edge of each aileron and linked to the main control through a calibrated spring. As aerodynamic pressure rose, the spring compressed, tilting the tab in the opposite sense to the aileron and producing an aerodynamic moment that helped drive the main surface. At higher speeds, the spring compressed further, increasing tab deflection and proportionally assisting the pilot, so stick forces remained almost constant across a wide speed range instead of ballooning with velocity. British test pilot Eric Brown later remarked that the Tempest's tabs made roll control feel unnaturally light at high speed, delivering roll rates that in conventional fighters would have required Herculean effort. He likened the sensation to having power steering before such systems existed, permitting precise, effortless inputs where other types stiffened to the point of uselessness. The system was refined through exhaustive wind tunnel work at the Royal Aircraft Establishment in Farnborough and months of development at Hawker's Langley Works, where engineers tuned spring rates and tab shapes to reap maximal force relief without inviting flutter or other aeroelastic dangers that could rip an airframe apart at speed. German units first ran into this advantage during the Normandy fighting, as Tempests began operating over the battlefield in growing numbers and combat reports described British fighters executing aggressive rolls and turns at dive speeds that left Bf-109s and Fw-190s virtually frozen by control loads. Hauptmann Joseph Preiler, one of the Luftwaffe's most seasoned aces, recalled an encounter over Belgium in September 1944, in which his Fw-190 felt like flying through concrete at around 400 miles per hour while the Tempest on his tail maneuvered as if it were barely moving. Even performing a barrel roll, he could not hope to match. Through the autumn of 1944, pilots' debriefs increasingly painted a disturbing pattern of technological inferiority. Time and again, Luftwaffe airmen described being outmaneuvered at speeds where they could barely hold straight flight. The problem hit Bf-109 crews especially hard because the type's cramped cockpit limited the sideways force a pilot could bring to bear. So crews, diving to escape, often found themselves trapped on essentially straight trajectories, while Tempests retained full control and followed them down. By November 1944, the situation had become serious enough that General der Jagdflieger, Adolf Galland, ordered a formal technical inquiry. Engineers from Messerschmitt and Focke-Wulf were tasked to sift combat films and wreckage for clues, initially hunting for some exotic hydraulic booster or radical, aerodynamic trick and overlooking a simple mechanical detail that had been dismissed in wreckage as nothing more than a trim tab. The truth only emerged in December 1944, when Luftwaffe technical intelligence at Rechlin examined a relatively intact Tempest forced down near a German airfield and uncovered the spring tab installation. The discovery provoked growing alarm because calculations, spearheaded by Dr. Friedrich Zimmermann of the Deutsche Verkehrsanstalt für Luftfahrt, indicated the tabs could cut control forces by as much as 70% at top speed. Zimmermann's report to the Air Ministry spelled out the stark implications. The enemy had fitted a control arrangement that delivered levels of maneuverability we had not thought possible, enabling their pilots to fight effectively where our machines had become marginal. He warned that fitting comparable systems to existing German fighters would demand extensive redesign and flight testing, a process that could take many months or longer. The revelation prompted a crisis meeting at Luftwaffe headquarters, in which Galland had to confront Hermann Göring with the uncomfortable fact that British fighters enjoyed a decisive technical edge that could not be remedied overnight, deepening rifts between Luftwaffe leadership and the Nazi political hierarchy over how to prosecute the air war. Germany's Axis partners in Japan suffered a similar shock when they encountered American fighters whose control systems kept them sharply controllable at high speeds. Imperial Japanese pilots found their manual-trimmed aircraft became almost unflyable in fast engagements with P-51 Mustangs and P-47 Thunderbolts, a disparity that Japanese ace Makoto Ogawa later described in his memoirs as being like fighting with one hand tied behind your back. When Japanese types like the Mitsubishi Zero and other IJN fighters ran into control loads that made aggressive maneuvers virtually impossible above about 300 miles per hour. Italian pilots in Mach C-200, Tafolgor, and C-205 Veltro machines tried various fixes, including linked aileron flap arrangements that offered modest help, but nothing matched the effectiveness of the British spring tab, so they suffered the same high-speed handling limits as their German allies. Squadron leader Franco Lucini, one of Italy's leading aces, repeatedly complained that the Machis turned into wooden aircraft at speed, forcing pilots to exert enormous physical effort just to carry out basic turns or escapes during fast engagements. Hawker began fitting spring tab ailerons at its Langley works in 1943 and refined the arrangement through intensive flight trials to find spring rates and tab geometries that gave large force reductions without creating structural or aeroelastic hazards. The first production run of roughly 100 Tempest V airframes included the spring tab fit, although a portion were briefly withdrawn in late 1944 after it became clear that the newfound agility could overstress airframes if pilots applied full control at critical speeds, so minor reinforcements and specific handling training were required. Sidney Cam and his team, mindful of the Typhoon's history of exhausting control loads, developed the spring tab in cooperation with aerodynamicists at the Royal Aircraft Establishment as a lightweight, reliable compromise that avoided the weight and complexity of hydraulic boosters. Building those ailerons demanded exacting calibration and individual flight checks to ensure the tab springs behaved correctly. Across the flight envelope, a level of quality control that became increasingly hard for German industry to match as shortages, dispersed factories, and the loss of skilled engineers took their toll. In 1944, skilled workers at Langley, many of them women, replacing men called to service, assembled the mechanisms to tolerances of thousandths of an inch, an attention to detail that literally translated into survivability at 400 miles per hour. The payoff was dramatic. Between December 1944 and February 1945, Tempest squadrons claimed some 239 German aircraft destroyed for the loss of only 20 Tempests, roughly a 7-to-1 ratio. That reflected not only pilot skill but the decisive benefit of retaining control, where enemy types were effectively helpless. Squadron leader David Fairbanks, the Tempest's leading ace, recounted how enemy fighters trying to dive away ended up locked into straight trajectories while he continued to maneuver for perfect firing angles, turning would-be escapes into slaughter. The effect on Luftwaffe morale was profound. Pilots felt they were outgunned by a handling advantage no amount of bravery could erase. A crisis of confidence spreading through units facing Tempest daily. Oberfeldwebel, Kurt Bulligan, of JG2, a veteran of more than 100 missions, wrote in January 1945 that they were fighting with yesterday's weapons against tomorrow's technology, describing the helplessness of watching Tempests dance at speeds where his FW-190 felt as ponderous as a loaded bomber. German efforts to copy the device were thwarted by material shortages, factory dispersal from bombing, and the depletion of experienced design teams, making the redesign and testing pipeline required for spring-tab retrofits effectively impossible. A few late FW-190 D-13s received hydraulic aileron boost as an emergency measure, but only a handful were completed before the war ended, and the added weight and complexity compromised performance elsewhere, a poor stand-in for the elegant spring-tab fix. Already hampered by fuel shortfalls, inexperienced crews, and numerical inferiority, the Luftwaffe found the control system gap another accelerating factor in its collapse. Pilots avoided fast engagements when they could, and operations such as Bodenplatte on the 1st of January 1945 were in part driven by a need to destroy Allied fighters on the ground, because meeting aircraft like the Tempest in high air combat had become increasingly suicidal. Captain Eric Brown of the Royal Navy, who flew and evaluated both Allied and captured German types, delivered one of the harshest verdicts because the FW-190 lacked spring tabs or a comparable aid. At top velocity, its ailerons were effectively useless. By contrast, the Tempest retained the crisp responsiveness of a trainer across its speed range, a deference Brown likened to wielding a precision weapon rather than a blunt club, and his assessment of the Bf-109G was even more damning, arguing that the narrow cockpit combined with crushing control forces turned high combat into a lethal trap where no amount of skill could substitute for sheer physical strength. Italian test pilots who flew captured Tempests after the armistice voiced similar astonishment, with Regia Aeronautica evaluators reporting that moving from a Mach-E to a Tempest felt like switching from a delivery truck to a racing car, especially at speeds that left Italian fighters requiring brute force to make even small control inputs. Major Adriano Visconti, one of Italy's leading aces, flew a seized Tempest in early 1945 and concluded that a spring-tab arrangement would have radically altered Italian fortunes in the Mediterranean had it been available. Japan's designers, who prized light, construction, and agility at low speeds, never produced an effective remedy for the control heaviness encountered above 300 miles per hour, leaving their fighters largely impotent against American types with superior high-speed control. Post-war interviews with Japanese pilots show many never fully appreciated the mechanical reason for the disparity, attributing defeats to opponent skill or mysterious technology rather than to the simple but decisive advantage of devices that preserved control authority across the speed range. Soviet engineers who studied, captured German hardware, and received technical information via Lend-Lease quickly grasped the importance of reducing control forces and began incorporating various remedies into post-war designs. Even if matching the British spring tab's elegance proved difficult at first, the Yakovlev Bureau in particular examined the problem closely, and Alexander Yakovlev later noted that the spring tab solved a problem they had been approaching from the wrong direction, informing improvements in later Soviet fighters. France's reconstituted aviation industry also investigated control systems after the war, with engineers concluding that spring tabs were among the conflict's most consequential but underappreciated innovations, a small mechanical idea that had decided many aerial contests without most participants understanding why. Marcel Dassault, whose firm would grow into a major European aircraft manufacturer, insisted future fighters include advanced control aids after seeing how control force limitations had crippled Axis air power. The production numbers told a stark story. Hawker had produced 172 Tempests by war's end, most carrying spring-tab ailerons, WHILE. German attempts to retrofit comparable systems yielded only a handful of modified aircraft before the Reich collapsed. Langley was turning out Tempests at roughly 15 examples a week by early 1945, each one another Allied fighter capable of dominating high-speed engagements as German factories struggled under bombing, material shortages, and the loss of skilled personnel. The human toll was severe. In January 1945, Alone, some 47 German pilots were killed in clashes with Tempests, a loss that equaled the experienced cadre of an entire fighter group and could not be replaced as training programs disintegrated. And novice pilots with minimal hours were thrown into combat. The psychological effect was profound, too. Word of the Tempests, near supernatural handling spread through Luftwaffe units, sapping aggressiveness and turning once bold pilots hesitant before a fight. Wing Commander Roland Beaumont, who led the first Tempest wing, later reflected that the spring tab was an ace up their sleeve the enemy had not anticipated, converting an already capable design into a dominant one by means of a simple mechanical innovation. Operationally, the spring tab paid dividends beyond immediate combat. Its mechanical simplicity made it more reliable and easier to maintain on forward strips than hydraulic boosters, and its small size kept drag penalties low compared with bulkier balancing devices. Ground crews could service and adjust the tabs with basic tools, while hydraulic systems demanded specialized support that was increasingly scarce for the Luft. Wind tonal work at Farnborough had refined tab size and placement to maximize force relief with minimal aerodynamic cost, and an added benefit was reduced pilot fatigue. Tempest crews could sustain longer missions or extended dogfights without the arm and shoulder exhaustion that plagued pilots in conventionally controlled fighters, widening the pool of effective airmen and lowering training washout. Technical post-war testing in the United States confirmed what pilots had reported. The FW-190 handled excellently at low and medium speeds, but became marginal above 400 miles per hour, and the Bf-109G's cramped cockpit made it physically impossible for many pilots to apply the lateral force needed for full aileron deflection. As the war stretched on, and veteran airmen grew rarer, the benefits of the spring tab became ever more decisive. While the Luftwaffe found many pilots physically unable to muscle their aircraft at combat velocity, the spring tab exemplified a distinctly British, practical engineering mindset, a compact, effective cure for a lethal handling problem rather than an elaborate technological indulgence. German designers chased heavyweight fixes, hydraulic boosters, variable geometry ideas, and other complex schemes, whereas British engineers solved the issue with nothing more exotic than calibrated springs and small auxiliary tabs, a difference of attitude that helped shape operational outcomes. The U.S. Strategic Bombing Survey later argued that such incremental technical edges accumulated into strategic effects well beyond single engagements, sapping morale and exposing how the Third Reich had slipped behind in key areas. The discovery of the spring tab undermined the long-held belief in German technical invulnerability and dealt a severe psychological blow. The idea did not die with the conflict. Variants and descendants of the spring tab appeared in military and civil designs for decades afterward, and modern systems that provide artificial control, feel, and automatic force compensation trace a conceptual lineage. Back to that simple wartime innovation. The episode also stands as a warning about the dangers of unquestioned assumptions. German confidence that only complex hydraulic systems could solve high-speed control blinded engineers to a far simpler solution, a blind spot that cost hundreds of lives and helped deny the Luftwaffe a meaningful contest of Allied air superiority in 1945. Survivors' accounts capture the terror. One pilot, who walked away from a Tempest encounter, described his Bf-109G going stiff and unresponsive at around 400 mph, while the enemy aircraft moved with almost balletic ease, a sensation he compared to being paralyzed while an assailant battered you. Excavations and archival material from Hawker's Langley works, even after later redevelopment, show how precision manufacturing underpinned the tab's reliability. Special jigs and fixtures, strict tolerances, and workers' recollections that management insisted a few thousandths of an inch could be the difference between life and death, emphasizing that these tiny parts were in practice life-saving hardware. The mechanism's wartime secrecy meant many Allied aircrew never fully understood why they had such an edge. Squadron intelligence were instructed to be circumspect if captured, and German collectors and analysts only grasped the tab's significance after tearing down wrecks, by which time it was too late to field an effective counter. Economically, the imbalance forced the Luftwaffe to pour scarce manpower and material into emergency responses, hydraulic retrofits, and investigations that diverted resources away from production and training. Unseen drain, at a moment when every hour and ton counted. For years, post-war histories spotlighted dramatic breakthroughs like jets and radar, often overlooking the humble spring tab, but more recent technical studies have restored its place in the story as a small, elegant innovation with outsized strategic effect. Ground crew's testimony adds a human angle. Mechanics, reported pilots, returning physically exhausted from fighting heavy controls, sometimes grounded for days by muscle strain. While Tempest pilots could sustain multiple sorties, Otto Bergmann of JG-26 recorded how flyers begged for any relief, even resorting to dangerous field hacks such as removing armor to shave weight. desperate measures that revealed the depth of the disadvantage. Above all, the spring tab saga highlights the value of steady, methodical development. The Royal Aircraft Establishment, systematic, wind tunnel work, and iterative refinement contrasted with a more improvised German response, and how cultural preferences for flashy, revolutionary projects can blind a technological community to simple, practical improvements that win wars. After the war, the spring tab idea proved adaptable, appearing on everything from commercial airliners to military transports and demonstrating that the simple concept Hawker used on the Tempest had much broader utility. Post-war airframes, such as the Douglas DC-6, adopted variants of the system, showing how wartime breakthroughs migrated into civilian aviation, even if their battlefield origins in 1944-45 were seldom acknowledged. In the conflict's closing months, Germany resorted to desperate measures to avoid combat unless pilots had superior numbers and altitude, and even the formation of ramming units, measures driven in part by the practical impossibility of intercepting fighters that could dominate high-speed engagements. The human cost was stark. Many replacement pilots had fewer than 50 hours flying time and were sent against tempests whose spring tab advantage they could not overcome. Training schools tried to prepare recruits for heavy control forces, but no amount of instruction could counter the basic physical limits pilots faced at speeds where Tempest retained full control authority. Surviving technical records from the spring tab program offer a clear window into methodical wartime problems. Correspondence between Hawker's design office and operational RAF squadrons shows an iterative feedback loop in which combat experience guided continual refinement, a process German manufacturers increasingly cut off from the front by worsening communications and organizational breakdown. Test pilots, such as Bill Humble and Philip Lucas, played a crucial role, pushing aircraft to their limits to find the best spring rates and tab Their careful test flights generated the data that ultimately saved many combat aircrews, and those reports remain in archives as evidence of the systematic approach taken. After hostilities ended, the technology spread internationally as former foes exchanged technical knowledge and adapted the idea for peacetime uses. German engineers who had failed to exploit spring tabs during the war later helped refine the concept for civilian applications, demonstrating how once contested ideas can be improved through post-war collaboration. Quantitative combat records back up the operational story. Engagement logs show Tempests achieving consistently favorable exchange ratios, particularly in high-speed fights where the control system gap was most obvious. So much so that a single Tempest could often engage several German fighters that were unable to maneuver effectively at combat speed. Manufacturing the system placed demands on metallurgy and production, had to retain precise characteristics across wide temperature ranges and endure millions of cycles. That played to British industrial strengths and became harder for Germany to meet as resource sources were severed and factories were damaged. That material shortfall compounded the Luftwaffe's tactical problems. Knowledge that Tempests held a handling edge reshaped doctrine. German units increasingly avoided the high-speed slashing attacks that had once served them well, ceding initiative to Allied pilots and forcing Luftwaffe crews into less favorable turning engagements where shortages of fuel, aircraft, and numbers proved decisive. Technical manuals and training materials distilled spring principles into straightforward diagrams and plain explanations, so pilots and ground crews with limited technical backgrounds could use and maintain the system effectively. A pedagogical clarity that contrasted with some contemporaneous, more abstruse engineering texts. Comparative studies conducted during and after the war show why the spring tab succeeded, where other ideas faltered. It offered the best mix of effectiveness, simplicity, reliability, and producibility. German trials of balance tabs, servo tabs, and hydraulic boosters demonstrated the existence of alternative approaches in theory, but none combined all the practical advantages the spring tab did under wartime constraints. Finally, REC inspections and intelligence files indicate German analysts were aware of tab-type surfaces by late 1944, but misread their importance, treating them as mere trim devices rather than a fundamental control aid. That misinterpretation of captured wreckage and combat evidence was a critical analytical failure that cost the Luftwaffe dearly in the final months.